Today we are going to talk about filters, in particular filters in frequency domain, because we could also build filters in time domain for certain reasons. Why are filters in frequency domain required? They are required to limit the noise in our receiver, to limit interference in our receiver, to limit spurious transmission out of our imperfect transmitters, and also analog filters are required in front of any analog to digital conversion, and analog filters are also required at the output of digital to analog conversions. Here is just as a brief introduction to filters, what we need filters for. We need filters in our receivers to limit the passband of our receivers, to limit the passband to the actual bandwidth occupied by the signal. This does not only apply to radio receivers, it also applies to receivers over coaxial cable or to receivers over optical fiber. Also in those cases we have to limit the bandwidth, to limit the amount of noise, and to limit interference from other users. The most difficult filters to build are antenna duplexers. What is an antenna duplexer? We have a transmitter and a receiver connected to the same antenna, operating all of the time. Both of them are operating at all of the time. This is in duplex mode. That's the reason why this is called duplexer. So we cannot simply switch the signal between the transmitter and the receiver. We cannot connect in parallel the transmitter output to the receiver input, because we would lose part of the transmitter power in the receiver, and worst of all, the burnout power level of the receiver is maybe 10 milliwatts, while the transmitter power here in the case of a radio transceiver is 10 watts or more. So the transmitter is 1000 times more powerful. That is the damage level of the receiver. So if I connected the transmitter directly to the input of the receiver, I would certainly burn out the input device in the receiver. These are the most difficult filters to build, are those used in antenna duplexer. Frequently they are used as they are designed as band stop filters. Band reject filters are usually here easier to build than the band pass filters. So band stop filters, BSF abbreviation here, rather than band stop filters. Low pass filters or bandpass filters, they are required in front of any analog to digital conversion, because here we have a fixed sample frequency, and of course we have spurious responses in the frequency domain at all multiples of the sampling frequency. So in order to avoid a multiple response of this A to D conversion of the sample and hold circuit, we need a low pass filter or a band pass filter. Here may also be a band pass filter. The same we need in the opposite direction. When we go from the digital world to the analog world, again we need a low pass filter or a band pass filter at the output of my digital to analog converter. Here analog filters are badly required even to get to the digital world. Let me explain this immediately. The real world is analog. We transmit analog signals over a radio link. We transmit analog signals over an optical fiber. But on the other hand, we are able to do some interesting signal processing in the digital world. I'm not going to talk about details in the digital world, but the digital world, strictly speaking, is an illusion. It's a mathematical illusion. We can do many things in mathematics, but they are all an illusion. The real world is the analog world, with high power transmitters, with low noise receivers, and we have to design this hardware, this analog hardware, analog front end. I'm not going to discuss much about the digital world here. The digital world is a world on its own. We can do anything in mathematics in the digital world, but it is not what we really need for communication. We can make completely analog communications, both receivers and transmitters, but the digital world always requires conversion to the analog world and vice versa in order to be able to be used for communication. So digital world is an illusion. That's the computer world, the digital world, and that's the communication world, the analog world over here, or over here. This is the analog world, and this is the digital world, the computer world. That's maybe a good illusion, maybe quite useful in some occasions, but it's still another subject that is not strictly part of our course. So that's the reason why I'm going to skip digital filters here, because they are not the thing we actually require for communication. For communication, we badly require any kind of analog filter. So what are the components of an analog filter? We need reactive components like inductors and capacitors. And with one inductor and one capacitor, I can make a resonant circuit, an electrically tuned circuit to a particular frequency. And this circuit stores energy in the form of oscillation. So this is oscillation circuit. Okay, also called oscillation. Unfortunately, this circuit has losses. Has losses mainly in the winding, in the resistivity of the wire making up the coil. Losses in the capacitor are usually 1 of 2 orders smaller than losses in the inductor. So the inductor is the main source of our losses here. Energy is stored in the inductor as a magnetic energy. Energy is stored as electric energy in the capacitor. Writing here things in the time domain. In the time domain, power, so immediate power lost in the resistor, we can also write in the time domain the power being dissipated in this resistor. The resistor represents losses in our tuned circuit. What is the important parameter of a tuned circuit? The important parameter, besides its frequency, we can choose the frequency by a suitable selection of the inductor and the capacitor. We can, the other important parameter is the so-called resonator quality. Resonator quality that applies for any kind of physical resonator. It also applies to an electrical tuned circuit, but the resonator quality will tell us how good a filter can we make with such a resonator. And in general, for any general physical resonator, the quality of the resonator is the angular frequency multiplied by the energy stored in the resonator divided by the average power in the resonator. So the energy stored in the resonator may be either stored in the inductor or in the capacitor, the sum of the two. But when the power in the inductor is maximum, the magnetic energy, the electric energy in the capacitor is minimum, and vice versa. So we can just calculate one of these, so maximum current squared times inductivity times the inductor, or maximum voltage times the capacitor. 1/2 because of here we have the energy has 1/2 in its formula. Same as in time domain. In the power loss, the average power loss, it's actually has 1/2 in front of here, because in the frequency domain, when we calculate things in the frequency domain, we usually state here maximum values, while for the average power, the effective value is important. So here is 1/2 of this peak power inside our peak power loss inside the resistor. For an LC tuned circuit, so LC tuned circuit, this general formula reduces to omega L divided by R. So we can simply express our quality of our resonator with inductivity, with the inductivity of the inductor, frequency, and resistance of the loss resistance here. So The Q of the overall circuit, as I told you, is depends. We have losses both in the inductor and the capacitor. They sum the inverse value of the Q sum together, the inverse value of the quality of the inductor and quality of the capacitor. I could define this separately, but it's only the inductor that's usually important. The capacitor is much smaller. So 1 over Q of the capacitor is the tangent of the loss angle of the dielectric, and the Q of the inductor is the inverse value here of this value here. This is just for the inductor. I intentionally removed here the capacitor quality because the capacitor quality is usually much higher than the inductor quality, so it doesn't affect much the sum here. What kind of electrical tuned circuits can we make? We can make an electrical tuned circuit with lumped components, with a lumped inductor, with a lumped capacitor. So I have an inductor with maybe a ferromagnetic core here, and I have a capacitor with some kind of dielectric in between. The resonant frequency is simply 1 over square root of LC for the angular frequency. If I want to resort to conventional frequencies, I have to divide everything by 2 pi. The quality such a tuned circuit can achieve is around 100. 100 mainly because of the resistance of the wire making up the inductor. Capacitor losses are usually smaller. If I need higher Qs, like for better performance filters, if I go up here, so I need better performance filters here or here. If I need a better Q, then I have to resort to another design technique. So if I build a coaxial cavity also has resistive losses in all the walls of the cavity. The walls of the cavity that represent my inductor, and the capacitance between the walls represent the capacitor of the tuned circuit. Here I can go with the Q up to 1000, approximately 1000 for coaxial cavities of typical dimensions for typical radio frequencies, typical applications for this. Unfortunately, cavities have also higher order resonances here. Higher order resonances going with odd harmonics of the base frequency. The same would really happen also in the lumped component, but we usually assume that lumped components are perfect. This is a perfect inductor, this is a perfect capacitor. In the real world, this is a distributed capacitor and this is a distributed inductor. So with distributed components, we also have higher order resonances. In the cavity, this is very easy to see, these higher order resonances. Usually, coaxial cavities are much taller here than their diameter. So R is much smaller than A if A is the length of the resonator. If we want to go even better than if we need a higher Q than 1000, we have to resort to a different kind of cavity. We have much lower resistive losses in a rectangular cavity, but this rectangular cavity is much larger than the coaxial cavity. So this really comes at the cost of the size of this cavity. And the rectangular cavity also has, say, for instance, for this mode of oscillation, the cavity has a capacitance between the top and the bottom plates of this cavity, surfaces of this cavity, and the side walls represent the inductivity of this tuned circuit. So again, I have the same electrical tuned circuits, but here I made the capacitor and the inductor in a different geometrical form. They assume a different geometrical form, but they still have exactly the same function. With a rectangular cavity, which is much larger than a coaxial cavity, you can see here from the dimensions, this is lambda quarter, this is lambda divided by square root of 2, so this is much larger. I can get the Q up to 10,000, Q to 10,000. And here the modes of this cavity, there are even more modes. If the cavity is larger, it has even more modes. So I have a simple formula how to correct modes L, M, N, where L, M, N are integers, and A, B, and C are the physical dimensions of this cavity, and C0 is the speed of light divided by 2. Here the electrical cavities end. Okay, we could make even much better electrical cavities using purely dielectric resonators, like sapphire resonators, made from sapphire or other expensive material, expensive crystals that have no metal in them. We only have electric field in them, and there the losses may be smaller, but those are exotic components. What we do if we need a Q larger than 10,000, if we can afford for space of 10,000, maybe we can afford this one, maybe we can only afford this one because of space and weight and cost constraints. A very good solution is to use a mechanical resonator. A mechanical resonator using shear waves in some kind of low loss crystals like quartz crystal. Shear waves, why? Shear waves because shear waves do not propagate in liquids or in gases. So this shear wave resonator has no losses of mechanical oscillation leaking out of these resonators, and if mechanical power is leaking out, we are damaging its Q. The same formula for the resonators is also valid for mechanical resonators. Here it may be mechanical energy, and here kinetic or potential energy, mechanical energy, and here maybe mechanical power loss. Also, mechanical resonators has multiple resonances. The most simple formula is written here, where we no longer have the speed of light, but we have the velocity of sound waves, shear sound waves in the quartz crystal. That's about 3.3 kilometers per second in quartz. Since this velocity is much smaller, the whole device can have much smaller dimensions than a rectangular cavity or a coaxial cavity for electromagnetic resonators. We can make this thing small with a huge Q about 100,000. Why are we using quartz crystal? Because quartz crystal is a piezoelectric. Piezoelectric means that we may have here coupling, immediate electromagnetic coupling to the mechanical oscillation in our resonator, and that's very useful to simplify the construction of this device. There are also mechanical resonators that have separate transducers from the mechanical domain to the electrical domain. Even here we have multiple resonances. We only have odd number overtones here, because even number overtones, they do exist in the quartz crystal, but they have no piezoelectric coupling. So that's the reason why we are not considering even mode crystals. We will have a separate lecture, since piezoelectric resonators are very important. In fact, silicon is not only useful for transistors. Silicon dioxide side, quartz glass, is very useful for optical fibers. But the third extremely important application in communications is the piezoelectric resonator, the quartz crystal used as a resonator. This is an important area of application of silicon, and this is the third reason why silicon is so important in communication. We will have a separate lecture just on piezoelectric resonators, so I'm no longer going to talk about them today, but maybe next time we are going to discuss piezoelectric resonators, since they are very required in many applications in communication. Now, understanding quality. The quality as we defined it here, we had all the losses. We have all the losses concentrated in this resistor that may be described mainly the inductor, but also the capacitor losses could be described in this resistor. Building a filter out of such a tuned circuits make things a little bit more different. So a filter is a two-port device, a frequency filter, where we add a generator that has some internal resistance or impedance, and we add a load. This tuned circuit is also loaded by the generator internal resistance and by the load resistance here. So it is loaded by both. So its Q decreases. So what we define right now on this picture here, that we are really talking about two Qs, two different values of quality of the resonator. We have the unloaded quality and the loaded quality of the same device, of the same resonator, that connected as a two-port device makes up a frequency filter, a bandpass frequency filter. The unloaded Q is where we short both parts of this two-port device. So all the losses are represented by the losses in the inductor, and maybe some small loss in the loss tangent of the dielectric of the capacitor, but this is usually much smaller. If it has much smaller effect than the losses in the inductor. When we use such a resonator in a filter, then its quality decreases. The loaded Q is always smaller than the unloaded Q, and the loaded Q also includes, besides the resistance of the copper resistance, it also includes losses in the generator internal resistance and in the load internal resistance. This Q is loaded, and this Q actually affects the passband of our filter. On many occasions, just to simplify things, I will say that the sum of the resistors now in our circuit is the generator resistance, the inductor resistance, internal loss inductor resistance, and the load resistance. And I will just indicate this as a sum of R, and so this is omega L. The Q loaded is omega L divided by all the resistors we have. So we should understand that while our resonator shorted may achieve a very high Q unloaded, the actual Q loaded of the filter may be much lower because of the generator and of the load here. We should understand these two qualities. Was it Q unloaded and Q loaded? And in fact, we are going to develop expressions where both of them will take part. This is what we can physically make with the best tuned circuits we can make, and the Q loaded is what is actually used in our circuit, considering all other components here in our circuit. So what is the response of such a filter? The response of such a filter, I can say that it is now the ratio of the load voltage divided by the generator voltage. Generator here at the contacts of the generator, the connections of the generator. And this is the well-known familiar resonance curve, and we are trying to get what is the bandwidth. The 3 dB, usually the 3 dB point is called the bandwidth of our filter. The bandwidth of our filter. Since I'm using here angular frequencies, I also express the bandwidth as a delta omega, so a delta of an angular frequency, to be able to omit the 2 pi here. So what is the 3 dB bandwidth? What is the Q loaded? The Q loaded, this is hopefully much larger than 1. Hopefully much larger than 1. I can simplify this expression here with just simplify this expression here. This expression just using the inductor and its nominal frequency omega 0. If I use the nominal frequency omega 0, I can try to find the simplification for this expression. This simplification here is dash plus minus j delta omega L. Delta omega, where delta omega is the whole delta omega, but I'm just half of this way in this direction, and I'm considering that delta omega is much smaller than omega 0, what usually is the case. Omega 0 is of course the resonance frequency of my tuned circuit. So the 3 dB bandwidth is simply connected to the Q loaded. The 3 dB bandwidth is simply the central frequency of my resonator divided by Q loaded if this is a filter, and it only makes sense to have a filter here. Or talking about frequency, the bandwidth here, I could write the bandwidth B or delta F here it's the same, but I'm just writing delta f to be compatible with this, is the reference, the resonance frequency f0, the central frequency of this filter, divided by Q loaded. So Q loaded is an important quantity of my actual filter. What is going to be the bandwidth of this filter? And this is actually going to be the request. The bandwidth of the filter is a request. I have to match the bandwidth to the bandwidth of my signal, not to distort the signal, and having the bandwidth the smallest possible to remove the largest amount of noise. So bandwidth should be larger than the signal bandwidth on one side, and as small as possible to reduce the amount of noise in my receiver here, up here. So the bandwidth of this bandpass filter should be large enough to let the signal go through, and as small as possible to reduce the amount of noise. So it is very clear what is required here. In this lecture I'm using, for bandwidth, I'm using delta f. So this expression actually is all what we need. But this expression is not exactly the way we would like to have it. The way we would like to have this expression, what we usually have, we know for our resonator what unloaded Q we can achieve. Then with our resonator we design a filter, and the filter has a certain Q loaded. So if we could express the properties of our filter just with Q loaded and Q unloaded, that would be fine. And that's what we are going to do here. So our generator has an internal impedance Zk. This is usually real, Zk. And we also have a load resistor that's also Zk. Usually we are considering filters in the matched environment. Although the filter is not matched, this kind of filter can never be matched to this environment, because the input reflection S11 and output reflection S22 are different from 0 even at the central frequency, even at the resonance frequency, they are different from 0. The impedance of this filter is different from 0 at omega 0. At omega 0 this cancels out, and it's even much larger away from omega 0. So if I express S11 or S22, because the network is symmetrical here, if I express it in the terms of scattering parameters, reflection coefficients and transmission coefficients are the usual way to do things in communication. So it's much more useful if we have a known characteristic impedance to talk about reflection and transmission coefficients rather than talking about impedances. We can express both quantities, calculate both quantities mathematically here. We can calculate both quantities, and now we have here we have some in the transmission coefficient, we have some insertion loss even at the resonance frequency when this equals to 0. There is still some insertion loss here, because the sum of all resistances is larger than 2 times twice Zk. And we also have some impedance mismatch for such a simple filter with just one resonator. A filter with one resonator will have some small impedance mismatch, so S21 and S22 is equal to 0. Now what we would like to have, we would like to replace these quantities here with the loaded and unloaded Q, and we are trying to do this here. So the sum of all resistors is the resistor of the inductor plus the generator internal impedance and the load internal impedance, 2Zk. Trying to express these things at the resonant frequencies. So this is actually omega L divided by QL for the loaded. For the unloaded case is this one here, and this is this one here. So now we are trying to find an expression for this long expression here for the sum of R here. We are trying to turn this formula around to find the sum of R here, and to plug it in here, because at the resonance frequency this term will vanish, but this ratio will provide us the insertion loss of this filter. And if we do this with the Q loaded and Q unloaded, the formula becomes very simple. That's quite an amount of turning equations around here, but the final result tells us what? The transfer function is always less than 1, and it's directly related to the Q loaded and the Q unloaded. So the insertion loss of the filter is a direct function of the Q loaded and Q unloaded of our circuit. And a very simple function. What does this function tells us? As long as the Q unloaded is much larger than Q loaded, the insertion loss of our filter is small. As we go with Q loaded towards Q unloaded, so we reduce ZK, or we design the resonator so that RCU is larger, then the insertion loss increases. If I express this thing as a power loss is proportional to the square of the amplitude transfer function here. So is this expression squared. As QL goes towards QU, my insertion loss goes towards very high, very low value. So I have very low transmission of this fiber, very high insertion loss I have here. Very high insertion loss intended as a reciprocal value of this 1/A. So this is minus decibels if I express this in decibels. So what I see here, I do not have complete freedom. I need a certain QL in my circuit. But QU, the unloaded Q, is what I can make. As long as the required QL is much smaller than Q, it's all fine. But as QL approaches QU, the insertion loss will become very high, so very low signal transmitted through my filter. So a filter with a very high insertion loss probably is not a good solution to be used in a receiver, and even worse in an antenna duplexer. So here it's very insertion loss, it's very undesirable here. So let's see. So we have to understand that Q unloaded is actually a limiting parameter of my filter design. I cannot design any filter with any component. I can only design filter that require a smaller Q loaded than the Q unloaded. And this is a technology issue, and that's the reason why I'm going to require resonators with higher Q. This Q100 can be used in some simple radio receivers, but that's all. More complicated radio receiver needs coaxial cavities, needs rectangular cavities, and I may need, for filtering the signal, I may even need piezoelectric resonators to filter some signals, when the requirement for the Q unloaded is very high. To have some reasonable insertion loss, not to having my signal vanish. And in any case, I can never go with Q loaded above Q unloaded. Q loaded is always smaller than Q unloaded, so this is the utmost limit. Even if I can recover any signal loss in my filter, this is still the limit of my device, of my filter. Finally, talking about filters, we have to understand that filters also have a group delay. Where the group delays comes from, if I have a tuned circuit, you see that this tuned circuit, it is ringing after the oscillation is started. This is still ringing for some times before the oscillation vanishes here. This ringing introduces group delay to my signals. So if I put in a modulated signal, this modulated signal will be delayed by its group delay of this filter. So the group delay is the minus derivative of the phase angle over omega. The phase angle derivative over omega. If I calculate this, I get the expression here for the group delay. The expression for the group delay comes from the phase angle of my filter response, and the phase angle comes out of my transfer function of my filter. Transfer function as we had it written here. If we were using S parameters like here, it is further 1/2 of this, because we are just taking this voltage in place of this voltage. So the group delay is also a quantity that's going to affect my filters. The group delay is frequency dependent. So it goes to very low values outside the passband of my filter, but it's very high inside the passband of my filter, and may distort my signals. It may cause intersymbol interference. So group delay, it's yet another problem we have. The different group delay, the differential group delay is a problem. If the group delay was flat, that was fine. It would not disturb signal, it would just delay signals. But if the group delay is a function of frequency, then it distorts my signals. The maximum group delay of the tuned circuit is defined by its Q loaded divided by pi divided by the central frequency. If I make this derivation at omega 0 at the central frequency, because at the central frequency of my filter, of my filter with a single tuned circuit, the group delay is the largest. In other filter designs, the group delay may be larger in some other regions, not in central frequency. But for a single tuned circuit, for this example here, the group delay is actually the largest at the center, at the frequency center. And this group delay may turn out quite large, especially for narrow filters. Narrow filters mean that the bandwidth is 1 over f0 over ql, the bandwidth of this filter. If the bandwidth is narrow, then this 1 over the bandwidth, the group delay becomes very, very large here. Now, how are we going to handle filters? Of course, this is not the ideal filter we would like to have. The filter that has such a frequency response like here. This filter, it's only a single resonator filter. We have this 3 dB bandwidth, but this 3 dB bandwidth may not be large enough to filter our unwanted signals, say here or here. So we have to resort to filters that have more than one resonator, not just a single resonator here, but having more resonators to build the required filters here. Okay, we can also concatenate filters here, putting amplifier stages in between. But even these filters here will not be a single resonator filter. These filters will include more than one resonator. How do we do that? So we do that using networks of many reactive components. Here in the simplest form, we arrange these reactive components into a ladder. So these are actually called also ladder filters, where we have series branches here denoted by their impedance Z, and parallel branches denoted by their admittance Y. Now Z and Y, we choose them for our filters, we choose them as reactive components. Hopefully as true reactive components, because we know that every inductor also has its losses. So we would like to have perfect inductors, and we do not. If we do not have perfect inductors, these losses will affect the passband and the insertion loss of my filter here. What is the response, the theoretical response of such a filter, such a ladder network? If it has identical Y component admittances and identical Z components, and all these are purely reactive components. Purely reactive components cannot absorb power. So if I think of this circuit as a transmission line, if this transmission line has a real characteristic impedance, then this is the passband of our filter. This filter will pass actually this frequency through the structure. But if the characteristic impedance of this transmission line is purely imaginary, then this frequency cannot go through this filter, because it's reflected back, sequentially reflected back on each component pair here. So this will be the stop band of this filter. This is a little bit different from the transmission lines. We already talked at this course about transmission lines. So with transmission lines, we had infinitesimally small components Z and Y. and we can calculate that for infinitesimally short sections of transmission lines. While in filters, this section have to have finite dimensions, finite values. And if I calculate the characteristic impedance here of, say, if I use T elements, if I distribute this into T elements, they writing like Z have, a T network and a Y parallel branch, Zk should be transformed into the same. Zk is that impedance, is the impedance that is transformed by such a network again in the same Zk. And so writing the equation here for Zk, I can try to solve this equation, and this equation for Zk has Z over Y plus Z half squared. What is the difference from the transmission line? In the case of a transmission line, these networks become, the T elements of a transmission line become infinitesimally small, and this term here vanishes. So a transmission line with these two reactive, if both are have J in front, if they are reactive, their ratio will be real. The transmission line always has a real Zk made of reactive components. While filter network, a ladder network with finite size Z and Y branches, has a characteristic impedance that has this term together, and this term here actually brings us some frequency dependence. When this term goes grows larger than these terms here, the square root becomes of a negative value, the square root becomes imaginary, and then Zk is imaginary. So when this is large, we have a real passband, like in the case of the transmission line. When this one is imaginary, so this one turns large, we have the stopband. So transmission lines do not have a stopband because the components are infinitesimally small, while filters do have a stopband, and that's what we want from the filters. We could also do the dual version of the T element, is the pi element. The pi element, we split the parallel branch into two parallel branches, and we have only one serial branch, and we have a characteristic admittance here, Yk. We should find this one here when this one is transformed by our network exactly in the same Yk. Also, the characteristic admittance, which is 1 over the characteristic impedance, has a similar formula where when this one is large, we get a real Yk, and when this one is large, we get a purely imaginary Yk in the stopband. So it's the same. So this is about the theory, very much simplified theory about building filters. Now let's look at some examples how to do these things. Look at the examples. Have first these things explained about the characteristic impedance that's real and it's imaginary. So what I said about the characteristic impedance, if we are building a bandpass filter, the characteristic, we have a passband here and we will have a stop band on both sides. Here in the stop bands, the imaginary part of we have an imaginary Zk, an imaginary characteristic impedance. While in the passband we have a real Zk. What we cannot do, what we can never do, is a rectangular response. A filter with a perfect rectangular response would require an infinite amount of components, and also an infinite group delay. We talked here about group delay. So group delay is a very simple way to understand why a filter with the rectangular response is impossible. It's impossible because this infinitely steep slopes would require an infinite group delay, and that of course is not possible with real world circuits. But further, we have other problems. We have a finite attenuation in the stop band, and that could be understood. And in the pass band, we have some ripple. Why? Because this Zk of the filter does not match the Zk of our system. We were talking here about the system Zk here, or say here, the system Zk here. So it's impossible to obtain a flat ZK also for the filter. So the ZK of the filter will be different from the ZK of our system, and that causes reflections both at input and output of our filters, and that will cause a ripple in the passband. If we have a lossless filter, the peaks of this ripple will reach unity. While if we have lossy components in our filter, like real-world inductors that have a resistance, then we have a finite amount of loss also in the best case of the transmission loss, where we do not have impedance mismatch inside this filter. So things are not perfect here, but we have to live with whatever we have. And here we have to live with ladders filters that we can make. There are methods how to reduce this ripple here. There are methods how to flatten the group delay to avoid distortion of the signals, but these methods, they do exist, but they are way too much for our lecture of today. It is much too complicated to consider it in the lecture of today. So how to make now filters? We have to start with the simplest possible filters. And the simplest possible filters, we can have inductors in the Z branch, in the serial branches, and capacitors in the parallel branches. This is a low-pass filter, actually. A low-pass filter, and you see that this ZK of a low-pass filter is a function of frequency. It becomes imaginary at high frequency. When omega grows, this term grows, and the square root becomes of a negative value. So it's imaginary at high frequencies, and it's real at low frequencies. So this is the pass band here of this filter, and this will be the stop band of our filter. A very simple low-pass filter, just plugging in the values that we have here, Z and Y. Z we have inductors, and Y we have capacitors. Of course, the dual example of the low-pass filter is the high-pass filter. We have capacitors in serial branches, the impedance of capacitors here, and we have inductors in the parallel branches. ZK is a quite similar expression for ZK, but now these things becomes imaginary at low frequencies. At low frequencies we have an imaginary ZK. At high frequencies we have a real ZK. So this low-pass filter is already something that is very required when we have analog to digital conversion. Then a low-pass filter is badly required here. So this is already a required component for analog to digital conversion if we want to do any digital signal processing. We also need a low-pass filter at an output of a transmitter to avoid radiating harmonics. We need a low-pass filter in optical communication to limit the wideband noise of our electronics. So it's frequently used. Low-pass filter is frequently used. The high-pass filter is also required for some applications. Making a bandpass filter now, it does not make sense to concatenate a low-pass filter and a high-pass filter. That does not make sense. Rather, building a high-pass filter with its proper components. So, mentioning about filters, the cutoff frequency is exactly the frequency when the characteristic impedance for lossless components here becomes zero. Here, both the imaginary and the real parts of zero, or infinity in some cases. Also here, for the T network they are zero, for the pi network they are infinite. Also the same for the high-pass filter, when at omega 0 the characteristic impedance of this filter is 0. The square root is exactly out of 0 at this corner frequency, cutoff frequency of this filter. It makes much more sense to make a bandpass filter using tuned circuits, so series tuned circuits for the series branches Z, and parallel tuned circuits for the parallel branches Y. There is quite an amount of calculation to do this, and we can calculate ZK with lots of patience out of components. So plugging these two values in the general equation we had here. This was the general equation. So we plug for Z and Y, we plug the values we have for the bandpass filter. The bandpass filter has two frequencies of zero impedance, so these are the two limits, the lower limit and the higher limit, depending on the plus or minus sign here. If we solve this equation, there's quite an amount of calculation in between here to get down to this result, but there are several issues we should address before getting to this formula. First, it makes sense how to choose, make a better choice of the frequencies, because we have actually two frequencies. We have the resonant frequencies of this circuit here, and we have the resonant frequency of this circuit here. Not to have here arbitrary choices, but to choose these frequencies, these two frequencies, resonant frequencies, to be identical. So that is the first choice we may have to make. And the other problem with such a filter is that we have these inductors for narrowband filters, and we usually need narrowband filters for radio communication. Radio communication is a narrowband application. These inductors may become very large, so they may be not implementable at the frequency of operation of our filter, and that is a huge problem. So these inductors may not be implementable. Well, capacitors, small capacitors are always implementable, but large inductors cannot be made for certain frequencies. So talking about the first problem, the problem of yet another degree of freedom here, since we have four components, four independent components, L1, C1, L2, C2, for actually three variables, Zk and omega 01 and omega 02. For three unknowns. There is yet a fourth unknown that is undefined here. Okay, let's choose the resonance frequency of these two circuits to be the same, and these things cancels out, like in the next picture here. So making a sensible choice so that the resistors and the capacitors are in the same ratio. If this is true, if the resistors are in the same ratio as the capacitors, then the resonant frequency of this tuned circuit, serial resonance, will be identical to the parallel resonance here, and formulas simplify very much. So from the complicated formulas here, we get to the simple formulas over here. We can very much simplify the formula for the characteristic impedance. We can also very much simplify the formula for the two critical frequencies where the characteristic impedance becomes equal to 0. We have the passband in between. The resonant frequency is exactly in the center, in the geometrical center of the passband. And we have a stop band with imaginary Zk below and above. So this is the usual design of a bandpass filter, and we can use this design as long as these inductors can be implemented. But this is not always the case. So this is a theoretical result, very good for wide bandpass filters, but almost useless for narrow bandpass filters, because we cannot implement these inductors here. So what we are going to do next, we are going to try to find the solution for this serial inductor. So what we are going to trying to replace this tuned circuit with L serial and C serial. So this is impossible because it's too large. It turns out to be too large, and large inductors have their own parasitics, have the capacitors between the windings, have its own resonances. So this inductor, we may make an inductor of large enough inductivity, but this inductor will have many parasitics that will limit its availability, its application. So this is actually impossible to make this inductor. How do we solve this problem? We put impedance inverters in front and after a parallel tuned circuit. A parallel tuned circuit is usually can be made because the inductance is small. How do we make impedance inverters with an S matrix of this form, 0, 0, 0 for S11, S22, no reflection, but we turn here the phase of the transmission in both sides. So to have an impedance inverter, this is actually a quarter wavelength line of selective characteristic impedance for the inverter. Ki means characteristic impedance of the inverter. So this actually inverts the impedance. It's a quarter wavelength line is inverting the impedance. We can do this in some filters for high frequencies where these quarter wavelength lines can be practically made. This is a practical solution, but at lower frequencies, when this quarter wavelength lines becomes unpractically large, we can make also LC impedance inverters like this one here, with C inverter and L inverter and C inverter and L inverter. This circuit also acts as an impedance inverter. Furthermore, actually now we hear these inductors may still be large. The L of the inverter may still be large. But in our circuit, actually, we have a parallel connection of this inductor and this inductor and this inductor. We have 3 inductors in parallel, and this is usually implementable. So this can be done, and this circuit here is actually what we can use for our bandpass filters, for our very narrow bandpass filter, because the CI can be made small enough. Of course, we have also no problems choosing ZK, because as I said you, this can be made small enough, and this is just a parallel connection with L parallel, so it can always be made. So this is the practical solution of the filter, and from this one we come out to a bandpass filter with no, actually this bandpass filter has no serial inductors, this cell here. Of course, this is only one cell actually replacing the series TN circuits. We'll have to connect in series many of such cells, but also for this cell here we can calculate its characteristic impedance. It's real in the passband between omega 0 and omega infinity. Our 2 frequencies, omega 0 and omega infinity, are of 0 impedance and of infinite characteristic impedance. Outside these limits we have the stop band, we only have imaginary ZK, and inside these frequencies we have the pass band of this circuit that has only real ZK. What we see here, this ZK changes even more than in the case of the filter with implementable inductors. So here ZK is changing very much, even here goes from 0 all the way to infinity. So this is maybe a slight problem, the changing ZK in this passband, but this is a circuit that can be made without non-implementable inductors. Without 2 large inductors we can make this circuit, and this is a real filter. Just to finish for this hour, how does such a filter look like, a practical? Here is a practical solution of this filter with a cavity. A cavity for about 450 megahertz is a quarter wavelength cavity. This is a central conductor. This goes installed into this can here. The can is the outside conductor. All conductors are silver plated. All conductors are polished on the inside to have the lower copper losses. And we have 2 adjustable capacitors here. So this cavity is actually really this circuit here, made with distributed components for high frequency, achieving a Q of over 1000. So this is a very good solution to make a narrowband filter for 450 megahertz here. So this is a solution, and this solution, this arrangement of capacitors, can be made perfectly matched on the desired frequency. We can choose all the components, so we have 0 imaginary ZK and real ZK exactly of the value of our system. So this filter can actually be made to work very, very well. So this is a good filter, and we can concatenate many such cavities to have a multi-stage filter to have a better response here. Okay, this is enough for this hour. Maybe there were lots of equations in this hour. In next hour, during next hour, we should also look at other arrangement of other filters. I'm going to show many such practical examples of how practical filters are being done in radio hardware, and mainly for radio receivers, transmitters. Other filters can similar filters can only be used for other purposes, but narrow bandpass filters are mainly part of radio. A to D converters usually require quite low pass filters. They are not as demanding as the narrow bandpass filters for radio. Also, optical communication does not require, at least at radio frequencies, does not require complicated filters. But optical communication may require very good filters at optical frequencies, and that's another another detail we cannot discuss in this course because it's way too much for this course.